Hello and welcome. My name is Hugo Curry and I'm a Year 12 high school student at the Riverina Anglican College in Wagga Wagga, Australia. This is a series of brief interviews with some of the most amazing physicists from around the world. I'm passionate about physics and will pursue a career in physics and engineering, so I'm honoured to be able to ask a few questions of some inspirational physicists. I really want to thank them all for generously taking the time to chat and, importantly, passing on their rich insights. Hopefully other students with an aptitude for physics can take inspiration and guidance from their experiences and insights to shape the next generation of physicists. Today I'm chatting to Professor Simon Cherry. Professor Cherry completed his undergraduate science and his medical physics PhD in London before moving to UCLA, where he developed co-registration techniques between PET and MRI, and also developed technology for high-resolution micro-PET for imaging small animals. He relocated to UC Davis, where he started his own molecular imaging and biomedical engineering laboratory. Professor Cherry is a professor in both the biomedical engineering and radiology departments, is co-director of the Explorer Molecular Imaging Center, and is distinguished professor in the Cherry Lab for Molecular Imaging Technology. Professor Cherry is responsible for developing the technology that allowed simultaneous PET MRI development, and he developed the first total body PET scanner called the Explorer, which is revolutionizing clinical and research in molecular imaging. He is widely published, including the lead author on several influential textbooks and book chapters. Professor Cherry has a very long list of prestigious awards, including the Paul C. Abersold Award from the International Society of Nuclear Medicine, Gold Medal of the World Molecular Imaging Society, the IEEE Mary Curie Award, and the Edward J. Hoffman Award. Thank you for taking the time to share your thoughts and experiences.
It's a pleasure to be with you.
So first off, how would you describe your journey to a physics career? Like, was it a direct path from high school straight to university and then to the career, or was it less direct?
It was actually a pretty direct path. So my dad's also a scientist, so I think that was the excitement of science was ingrained in me from a pretty early age. He's in a somewhat different field, but growing up, one of the things I was really interested in as a young boy was astronomy. So I had a telescope, and so that was the sort of side of physics I was really engaged in at the time. And so when I went to university, it was a pretty easy choice that I wanted to study physics. And in fact, my undergraduate degree was physics with astronomy, so it sort of combined the two things I loved. And sort of never looked back from there. And I think I always wanted to be in science. I always wanted, if possible, an academic career. I love the freedom, being able to come to work each day and pretty much do whatever I want to do. It's a remarkable job to have. And then how I got into medical physics, more specifically, was really, after I finished my undergraduate degree and I was looking to go to graduate school, I was trying to decide which area of physics to get involved in. And there are so many great areas in physics. It's a pretty tough decision. I was particularly drawn at the time to high energy physics, nuclear and atomic physics. I was still very interested in astronomy and astrophysics as well. But the challenges in some of those fields are, the experimental teams are huge. You're a small cog in a very large wheel. And I felt, it'd be hard to get sort of the breadth of experience I was perhaps looking for. And I sort of discovered more by chance than anything else, there was this sort of subfield of medical physics where, you could apply the principles we'd learned in physics towards disease diagnostics and treatment. And that really intrigued me. I didn't know much about it at all. And I have to admit, when I went for interview for PhD positions for specific projects in MRI and in PET imaging, I gave some pretty poor answers to the interview questions because I really did not know much about the field at all. But somehow, luckily, I got accepted into a project on positron emission tomography PET imaging and never looked back from that point forward. So that's sort of how I got there.
Yeah, nice. So linking the so you said that you kind of didn't see a field and it kind of wasn't known, but when you got into it, it was well worth like being part of it. In that way, what do you see as some of those fields on the horizon for the next generation? Like, what are some of the niche sort of areas do you think that might interest next generation of physicists?
That's a really good question. It's always hard to predict where the next big advances are going to come. In physics, really influences so many different fields, and I think it can have applications in pretty much all the major areas of a challenge that we see. Climate change, energy production, lots of different areas where physics is going to play an important role in the future. So it's hard for me to pinpoint any one of those. I will say that I think within sort of my own area, there's still enormous opportunities for physics to impact our understanding of biology. Bringing some of the approaches we take into physics and some of the computational modeling, and bringing that into biology and working at that interface. I mean, biological systems are incredibly complicated. Yeah. And we need people with those kinds of skills, I think, to really study some of these systems. So I think there's so many opportunities. I would hesitate to say, it's this one or that one. I think you follow your passion. If you love physics, you look at the different areas it's being applied, and the things you're most interested in. If you want to help human health, for sure there's areas there. If you want to help the planet, for sure there's areas there as well. And fundamental research is equally important. It's very easy to get caught up in applied research and it's sort of immediate impacts of physics that physics can have in those areas. But we need to continue fundamental physics research as well, because that's going to be the underpinnings of future developments we can't even conceive of right now.
Yeah. So what skills have you relied on most throughout your career as a physicist?
That's, it's a range of things, and some of the things are things you don't really get taught necessarily. So, working in an academic environment, obviously I lead a fairly large research team. And so I think, one of the things you learn there quite quickly, and which, I had no formal training in, is how to manage people, and how to support them to achieve the best that they can achieve, and to create a productive and supportive work environment for them. And it's something you sort of learn as you go, how to pick the right people to work with, because the different personalities, different labs have different cultures. So bringing in the right people that fit well and don't disrupt the culture but add to it.
Yep.
I've always liked having a wide range of people from across the world. We have pretty equal gender representation in the lab. Having this mix, I find very healthy and very productive. So that's been good. So I think the people management side is something I probably didn't appreciate going into this at all, and it's something I've had to learn as I go along. Education is a key part of what I do as well, and I had no formal training in how to teach either. I just had to one day, walk into the classroom and start lecturing. And, that's a whole skill, as I'm sure you will appreciate. You'll know you have some teachers you love and some teachers you don't like so much. So how to get students excited about, the field that I work in, and how to get them engaged in the material, and how to interact with them to make it a great experience for them. So these are some of the things that I've sort of picked up as I've gone along that perhaps I didn't appreciate when I started out in my career would be important. And then, of course, you combine that with, hopefully, with the sound basis of the physics that you learned in school and university as well, and bring all those pieces together. And then I think also, just passion for what you do is really, really important. If you don't enjoy it, you're not going to convey that to others and bring them along with you. So you got to enjoy it.
Yeah, I agree. I mean, I've got a few friends at school who didn't enjoy year 10 physics, and so didn't pick it as an elective in our senior study. But there's such a massive difference between the two. Year 10 physics being simply like velocity time diagrams and
Mhm.
simple things like that. But once you get into year 11 and 12 physics and you're talking about atomic nuclear particle physics, electromagnetic induction, things like that, it's so much more interesting. And they're sitting there going, oh, I should have picked that. But I found that, yeah, if you don't enjoy it, at least in the start, you won't stick with it. So
Yep. Yep.
So you've had such an amazing career. I'm interested to know what you would call the highlight.
Well, that's a hard question too. I think for sure the biggest highlight is recently with the development of this total body PET scanner, one that's actually sitting behind me here on the screen. And and I think because it took so long and was so difficult to convince people to fund the project and support the project, that's why it's a big satisfaction having now finally brought it to fruition. It was a 15-year process. So I think probably that that really is the highlight. But there are others too. I mean, I remember when we built our first small animal PET scanner. So it was really the first complete imaging system my lab had put together. The moment you get that first image is absolutely a great moment. And you mentioned in the introduction the the sort of combination of PET technology with magnetic resonance imaging, MRI, and building the first very crude prototypes that could acquire both signals simultaneously, and getting those first results also was a big moment. So I've been really fortunate to have a number of those really exciting moments. And then there are other moments that make you really proud when when one of your students or postdocs go on to do really well. You see them a few years later get up at a conference and present some amazing work, and they started out in your lab, and that's a really nice feeling too. So I've been lucky that I've had some great trainees that have come through the lab.
Yeah. So you and your team developed the total body PET scanner, which is a game changer for clinical and research practices. What inspired you, and how do you take an idea like that from imagination and then develop it into reality?
It could be a very long story. That I'll keep to the short version. I think if you can summarize it in one word, it's perseverance.
Yep.
So I mean, the idea of doing this is not new. I mean, you can trace the idea back in the literature to the 1980s or so. I mean, so the concept is that we're trying to image these radio traces that are injected inside the body, and the radiation's being emitted isotropically in all directions. So if we want to efficiently capture that radiation, then we need to surround the patient with detectors that can geometrically cover that whole volume, or as close to all of it as possible. And then the other side benefit of making a scanner that really covers the entire body is that you can see the entire body at once. So you can actually image all the tissues and organs of the body simultaneously, and that's never been done before. So the challenge had been out there for a while. There were a number of things I think prevented people from doing it. Certainly, the technology had to mature to a certain point to make it possible. Perhaps more importantly, the computational infrastructure needed to be there to support these very large data sets and to be able to reconstruct them. So I think that was another impediment that would have stopped it being done a lot earlier. But probably the biggest impediment, surprisingly, really was I think a fair amount of resistance in the field, a fair amount of skepticism that it was worth spending this kind of money, and maybe this is a little controversial, but I think that's a bit short-sighted. I think you really need to push at the frontiers of every field to see what's possible and to learn. If we're able to collect a lot more information, what can we do with that? That doesn't mean that every hospital needs to necessarily have to have, a total body PET scanner. It's sort of the Lamborghini of PET scanners, right? It's not that necessarily every hospital needs one, but it shows us what's possible, and it will drive innovation in the future. And if cost is the only barrier, and we show there's huge advantages to doing this, then we'll find ways to bring the cost down, I'm sure, with time. So yeah, we had a heck of a time getting this project funded. That was the main. We could have done this project back in 2005 to 2010, which is when we were first pushing for it, and we just had failure after failure in terms of grant proposals that were seeking funding to support it. I will say part of that is our fault and responsibility as well, in the sense I don't think we really did a good job of projecting the applications, both the research and the clinical applications. We didn't make a strong enough case in the early days, and that's something that we learned over time. And we've really built a good team, I think, to develop the concept. You know, I particularly want to mention my collaborator, Ramsey Badawi, who co-led this project from the very start with me. So it was actually a conversation between him and myself shortly after he joined UC Davis that led us to deciding, yes, we were going to do this. We were going to tackle it and try and do it. And then also, you know, one of the pioneers in the PET field, Terry Jones, who we pulled into the project, who really knows a lot about the applications of PET, has been, you know, often the pioneer in using PET in different disease areas, and he really helped us strengthen the clinical and the research case for developing the technology. So, so it was a long journey, and the key thing was not to give up. I mean, the key thing was, yeah, we knew it was going to make a big difference. We knew it was going to open up new opportunities. And so we were determined to do it. And, you know, we spent a lot of years in the wilderness. And of course, we were doing other things as well because we had to keep supporting ourselves while we didn't have money for this project. But eventually, I think maybe we wore everybody down, and we got a large grant from the National Institutes of Health. And then I think you know, interestingly, then another challenge hit, which was suddenly we realized, okay, we've got this large sum of money to build a prototype, fabulous. But now another big problem presents itself that, you know, the whole field is watching us. We just got this large sum of money, and we better make something that actually works and lives up to the promises that, you know, we had put forth. And, you know, if you think about an academic lab, you know, building something on this scale on its own, it's a frightening thought. So we realized very quickly we better get an industry partner who, you know, had experience in manufacturing. And so that was sort of the next big hurdle, was to find a company that would really work closely with us and take the idea from concept to an actual system that would work, and also that could be commercialized. Because again, if, you know, taxpayers pay for one prototype to be built at one institution, that's not going to impact, you know, healthcare nationally or globally, right? So if the system was as successful as we predicted it would be, there needed to be a commercial outlet as well. So that was the other reason to engage industry. So, but fortunately, we found a great partner in about 2016 who helped us develop the first system, and it's now commercialized, and there's 7 or 8 of them in the world now, and more coming, I hope.
Yeah. Yeah, I interviewed Professor David Townsend last week, and he was saying similar about his development of the PET-CT system.
Right.
Yeah, there was a lot
very
of
similar story, I'm sure.
Yeah, a similar resistance, I think, as well.
Mm-hmm.
So I understand you did your postdoctoral years in PET at UCLA.
That's correct.
How did working with Ed Hoffman and Michael Phelps shape your career?
Well, of course, you know, UCLA was sort of one of the meccas of PET at the time. You know, incredibly strong program. You know, Mike Phelps, very visionary leader. He always seemed to be able to see over the horizon to what was, you know, coming in the future, and really challenge us to think big. So that was very, very stimulating. You know, Ed Hoffman knew the physics of PET inside out. Great mentor, just had the right touch of, you know, enough guidance, but enough stepping back to let you develop your own ideas and concepts. So I learned a tremendous amount from both of them. I couldn't ask for better mentors. And then it wasn't just them. I mean, there was just an amazing group of people at UCLA at that time in different areas, in neurology and cardiology and nuclear medicine. And so I learned a lot of the clinical applications and the research applications. So it was a great time to be at a great place. And, you know, I was somewhat fortunate to be there at that time. It was really a great experience.
Yeah, no, definitely sounds amazing. It's I think there's a lot of value in a great team and mentors as well.
For sure.
Is there anything in physics that's important or contentious that you would like to see the next generation of physicists work on?
Well, I mean, important, there's many things, right? And it comes back to some of the things I said earlier. Obviously, you know, our planet faces some massive challenges that we all know about. Physics can and will play an important role in addressing those. There's many roles for physicists, whether they be experimental physicists, computational physicists, physicists that do modeling. You know, there's many opportunities there, and so we need good people on these big problems. And then in the sort of health biology arena as well, we still have a lot of unknowns. There's a lot of things we don't understand about the human body, and of course, some of that understanding is going to come from biological studies, no question. But you know, the body is incredibly complex, and when we start to think of the body as a system of interacting, you know, organs and tissues with communication going on between each of the tissues and organs, you know, this is very amenable to highly complex modeling approaches, which physicists are very good at, and also the amounts of data that are coming out of studies of biological systems also lends itself well to some of the techniques that we use in physics. So I think there are lots of opportunities at the interface of physics and biology, and so I'd like to see more physicists jump into that area. And then again, you know, fundamental physics, you know, we have the standard model, but you know, there's data from, you know, the muon G-2 experiment that's starting to call that into question, and so there's still a lot of work to be done there as well. And that seems very abstract in terms of, you know, how it's going to impact us, but you know, as we understand more and more about, you know, fundamental physics, that will trickle down to many applications, I'm sure. And then, you know, energy production is another obvious area, you know, how we can improve, you know, energy production, clean sources of energy. So those are just some of the things that come to mind. There are many big challenges out there that physics and physicists can contribute to, which are very meaningful.
Yeah, I think physics is one of those fields that is everywhere, can be used for everything.
You just have to look. It's not always obvious that it's everywhere, but you're absolutely right. It is everywhere, and there's roles for physicists in just about every area of science.
Yeah. So the final question, do you have any final pearls or pitfalls to offer high school students that have an aptitude for physics?
Follow your passion.
Yep.
You know, get exposed to as much as you can. So, you know, look for where physics is being used. We just said that, you know, it's not always obvious where it's being used. So, you know, take the chance. I mean, there's so much material online these days. There's great lectures online. Actually, COVID sort of helped this in a way because so many people have been recording material and putting it on the internet. So there's tons of great material that have been produced over the last couple of years. And so you have to take advantage of that. You know, if you can get internships or volunteer positions in labs, you know, do that, because that gives you great exposure to what it's like. So, you know, my lab has taken high school students just prior to them going to university for sort of summer experience, and I think they've enjoyed that and got a lot out of it. So yeah, just look for all the opportunities out there. I mean, you know, labs like mine are only too happy if somebody comes to them with some interest and wants to learn more. I mean, it's always an honor to help people follow what they're interested in. And then, you know, physics is not easy. I mean, it's, you know, we know that some of the stuff in physics is hard. And you sort of mentioned that, you know, some of the early courses in physics are a bit, you know, dull and monotonous, and that's true. And you sort of have to get through that material so you can build on it. But there are big rewards at the end if you do, because then you get into the really exciting and cool stuff. So it's worth taking that time. So perseverance and passion, the two P's, I guess, is my advice.
Awesome. Well, thank you for such a rich insight into the world of medical physics and biomedical engineering. I really appreciate you taking the time to inspire the next generation of physicists. I'm sure that those that listen will share my appreciation. Yeah, thank you.
That was my pleasure, Hugo. Enjoyed it very much. Thank you.
All good.